That is a rate. This is a rate ratio. So when someone tells you an item is coming out of a container of some sort at however many milliliters per minute, what is that? That's a rate. That's a rate of effusion. They're telling you how fast the thing is escaping. That's a rate. Isn't that true? Some rates are slow, some rates are fast. But that's a rate. Is that correct? Now, what if somebody tells you that they're going to compare these rates? If you put a fast one over a slow one, what's it called? A rate ratio. So the conversation is about a competition of gases getting out of a container. And the equation is that the rate ratio, the fast over the slow, is going to be equal to the big molecular weight, and then you just crisscross them, the molecular weight of the slow on the top. Just remember fast over slow. And then invert them on the other side. You good? Okay. Helium diffuses. Helium escapes 3 times faster than gas X. What's the molecular weight of X? Helium escapes 3 times faster than gas X. What's the molecular weight of X? What is this? What's that? A rate or a rate ratio? Oh yes, a rate ratio. It's this one. They already gave it to me. That's a rate ratio. When you tell me something is that many times faster than something else, you're already telling me the ratio. He runs twice as fast as me. Did I tell you his speed? No. Did I tell you mine? No. What did I tell you? The rate ratio, that line. So that means 3 equals what? Where does the 4 go? On the molecular weight of the fast. And what's this? The slow one. We good? That's it. The chemistry problem ended here. That's the end of the chemistry problem. What's it called from this point down? Algebra. That's somewhere else.
Where did the 4 come from?
I don't know. Somebody told me 4. Where did the helium come from? The helium, molecular weight of the helium. Where do they all come from? All right. The chemistry problem, y'all, ended here. The chemistry problem ended here. From this point on, it's algebra. So for the sake of argument, let's suppose that we wanted to go ahead and finish the problem, which I shouldn't, because you should know how to finish it. But let's suppose for the sake of argument that I do want to finish it. What's my next move? Oh, thank God. Square both sides. All right. And then what?
9 equals x over 4. Multiply by 4.
Step away from the calculator. There you go. We good? And all of Graham's law problems are about telling the difference between 3 things. Rate, rate ratio, and the third one is time. Time. What are units of time? Seconds, days, hours, etc., right? Etc. What are units of rates? Milliliters per second. Milliliters per second. How about gallons per year? Sure. Something could be escaping at a rate of several gallons per year. I don't know that. So I can imagine that there's going to be a lot of shenanigans surrounding units. A lot of shenanigans surrounding units. And now, tell me, what are the units of a rate ratio? And what's a rate ratio? What's a rate ratio? The division of two what? Two rates. So if you park a rate in the numerator and you park a rate in the denominator, what happened? No units. Unitless. They cancel. They cancel, of course. Is that good? A gas effuses out at a rate of 1.7 liters each week. How long will it take to escape? How long will it take for 25 gallons to escape? What's the question? Time, rate, or rate ratio? Or molecular weight? What's the question? So that unit is going to be an answer of a unit in regular time units. Is that correct? Okay. So tell me, what's this? What's that? A conversion factor. That's your rate, a conversion factor. So how do I start? And how do you know that you should start from this one? It has the 1 unit. So hit it, 25 gallons. Times, I may be totally clueless, but I know it goes down here. What?
Gallon.
Mm-hmm. Hit it. Let's go. You're already taking too long. Let's go. What's the hold up? What? 1 gallon is 4 quarts times. My hands are tied. My hands are tied. My hand writes this by itself. I have to actually hold it because it wants to write quarts down here automatically. It writes itself out. Hit it. What do you got? That 1 quart is what? 0.946 liters. Is that correct? And now, I may be totally clueless, but I know it goes down here. 1.7 liters. And 1 week. So the time unit that you're going to get at the end of this problem is what? Week. So can you imagine the same problem if somebody were to ask you days, time, days, years, hours, seconds, and so on? It's all about the units. All about the units. So the last conversation that I want to have about gas laws is kinetic molecular theory and ideality of a gas. Ideality of a gas. We talked a little bit about this. We talked about the fact that there is no such thing as an ideal gas. No such thing as an ideal gas. But there is ideal gas behavior, though. Is that correct? Ideal gas behavior. Describe to me what an ideal gas is like. What would be the ideal conditions for a gas to behave ideally? Well, I'll tell you what. It would obey PV equals nRT. Correct? And for that to be able to happen, it has to have, tell me about the temperature, pressure, and volume. It doesn't have to be constant. No, it could change. But I want to know under what conditions would a gas behave ideally? What are the ideal behaviors of a gas? That it moves in straight lines in direct proportion with the absolute temperature. That it exerts pressure by colliding against each other on the wall of the container. That they are discrete particles that don't particularly attract or repel each other. Remember, please read. I can tell you guys haven't read this yet. This, you know, test 3 is going to be a repeat of test 2. If you don't read ahead, you guys are behind. Discrete particles that don't particularly attract or repel each other, like styrofoam balls inside of a vacuum cleaner. So tell me, what would be ideal temperature, pressure, and volume for a gas to behave ideally? Temperature, high or low? I want to put high and low underneath each one of these things. For a gas to behave ideally, high temperature or low temperature?
High.
Oh, absolutely, high temperature. Because if you drop the temperature, what might happen to that gas? It'll condense. It'll become a liquid. And liquids are not very good ideal gases. So of course you want the temperature to be sky high. What do you want the pressure to be? Yeah, because if you compress a gas, what happens? You compress it into a liquid. You know that. So of course you want the pressure to be as low as possible. Let the gas expand as much as possible. How about the volume of the container?
High.
High. Let a gas be a gas. Let a gas be a gas. So under those conditions, ideal gas behavior is likelier. Do we understand that? Kinetic molecular theory of gases. Kinetic molecular theory. Is that okay? Alrighty. Chapter 4. Chapter 4. In chapter 4, there is some parts of it that you already, there's some parts of it that you already know. And that, you remember the electronic distribution? Yep. Ideal behavior of it. Ideal behavior. Alright, chapter 4. Atomic theory. So what I want to do is I want to go through some of the history with you guys just very, very briefly. And we'll do the equations in, try to do in chronological order. Okay? A little bit in chronological order. A lot of the times when you grab these chapters, and believe me, you're having about the same experience most students have. You read the chapter, you read through it, memorize a whole bunch of equations, you hope the algebra works, you grab a calculator and hope for the best. It's true. It's true, right? But I'm going to ask you something. For chapter 4, please make a conscious effort to read through and remember the names of the individuals, because they are often on exams. Not just the one that I can tell you will be on. I will ask you for the names of the people. Okay? But in the future, you're going to expect that you know some of these names. Okay? So we're going to start in 400 BC. 400 BC. BC, eh? Yeah, I know, right? Chemistry didn't start. Chemistry didn't start very, I don't know what to say, very glamorously. It wasn't very glamorous. Chemistry, the word chemistry, it stems from the Arabic alchemia. Alchemia is the study of the black dirt. Okay? But listen, that name came in the Middle Ages. Back, 400 BC, in the Greek culture, people were already starting to ask, what is everything made up of? You know my favorite example of Og and Grog walking around, stumbling over things, and going, ugh. Look, it is human nature to ask, what's that? And what do people do when they don't know what that is? What's the first thing they do? They throw something at it. They grab a stick and they poke it. They grab a rock and they throw it at it, just to see what it does. It's human nature. Of course it is. The Greeks were starting to ask these questions, and they were starting to formulate theories. And a very popular one was that everything was made up of 4 elements. Come on, you know them.
Fire, air,
Now I'm
earth,
a certain
and
age.
water.
I'm of a certain age that I have to say these in order: earth, wind, and fire, and then water. Okay, I have to say those in order. Earth, wind, and fire, and water, of course. So everything was made up of different amounts of these elements. And it worked beautifully, and it answered questions for thousands of years that way. For example, why does a rock fall to the ground? Gravity. What's that? What is that? Whoa, what's that word? Well, you know, a rock, let's pretend this is a rock, falls to the ground because it wants to go home. Because rocks, I lost my rock there. Because rocks occupy the lowest level in the natural order of things. Because in the natural order of things, the bottom layer is rock. I've seen it. Because everything in my environment, the rock is the bottom layer. And what's right above the rock? Water. Water. What's above the water? Air. Air. Yeah? Whatever that is. And what rises above air? Fire. I've seen it. I've seen it. Why does paper burn? Because it's partly made up of fire. And I see the fire come out of it. I've seen that many times. You know I can keep this going, right? Why does something made out of a mashed up tree take so long to reach the floor? Because it wants to stay partly at home. It contains fire, and fire keeps it afloat. And all I have to do is set it on fire, and I can see the fire come right out of it. Right? Now, I'll tell you what, though. I'll tell you what an example the Greeks probably never did. Can I borrow this? I could tell you something they never did. If I throw a rock to the ground and a paper to the ground, who gets there faster? The rock. Why? Because the paper wants to stay home. I bet you they never did this one. Because when you remove the buoyancy from the air, all objects on this third rock from the sun fall at the same rate of speed with the same acceleration. You take away that, and that paper goes down just as fast as a rock. I bet you a nickel that the Greeks never did that. I bet you a nickel they never did that. So, who started saying things like matter is made up of atoms and actually made up the word? A guy by the name of Democritus. And he gets up and he says, hey, I have a new theory. And you know how the philosophers get together and philosophize? It's true. It's true. And he gets up and he says, hey, I have an idea. And he says, I think that matter is made up of tiny, indivisible little particles. Yeah. And all of these indivisible little particles give the physical property to the matter that they make up. So atoms of air are fluffy and light. That's why these items are fluffy and light. Atoms of water are slippery. That's why they run through your fingers. Atoms of fire are prickly. So when you touch them, it hurts you because they're pricking your finger. Brilliant. Brilliant. Of course, it's utter nonsense. But it was what they had. And the explanation began. Humans began to ask questions. Why? And if a theory wasn't working, they came up with new ones. And they had a chance to run it around the world, telling other people, and other people gave their opinions and said, I don't know about this prickly air molecules and fire molecules and atoms. I think that's a little weird. Thing of it is that Democritus was pretty ignored. But to the Greeks' eternal credit, they wrote stuff down. And to the eternal credit of the bands of humans that went through there, burning libraries and things like that, some of them kept the information and passed it along. So in the year 2014, you know about Democritus, so that otherwise you would never have known about him. So the first person to ever talk about atomic nature of matter, the basic Lego blocks, it was a guy by the name of Democritus. So, the next year that we're going to go to is the 1600s, in the 1700s. That's a jump. 1600 to 1700s. This is a very exciting time. This is the time of Galileo, of Copernicus, of Kepler. What did those guys do? Thank you, Captain Obvious. Can you be more specific? Tell me one thing you know about Galileo. We're gonna visit his museum in Italy when we go in May. So if you remember, if you got my email, go to the Study Abroad Fair this Wednesday. What did Galileo do?
Rotation of planets.
The rotation of planets was this one. Was that guy? This is the guy that described the orbits of planets and things. Kepler, Johann Kepler. What did Copernicus do? Heliocentric theory. What did Galileo do? Mostly agreed with him. mostly got himself into a lot of trouble by saying, this guy's got a point. And who got mad at him?
The church.
Yeah, the church. And what did they do to him? No, they did not. Did they torture him? No, they did not torture him. They didn't do any of those things. They put him on house arrest. Where? In a villa in Tuscany, and they gave him an assistant. Right? Okay. Galileo, that was the blind guy. The one that went blind looking at the sun through a telescope. Okay. Towards the end of Galileo's life, listen to this. Somebody mentioned gravity before. Gravity was nothing but a whisper. It was a whisper. Galileo didn't have any proof for what he was saying. It's also probably not true, by the way, that he threw anything off of the Leaning Tower. It's nice to think that, but it probably didn't happen. Only because if he had done it, he would have said it himself, because he was like really a big deal by talking a lot. He was a very popular guy. He insisted on writing in Italian rather than Latin so that the people could read. So he would have said it if he had done that. The year is 1642, and gravity is just for a whisper. And Galileo is dying. He dies in 1642, in the same year, in a farm about 100 miles north of London. A woman gives birth to a baby who has lost his father. And she names him Isaac. Yes. Think about the baby was born on Christmas Day, on December 25th, 1642. Think about that for a moment. In humanity's history, Galileo dies the same year that Isaac Newton is born. I don't know about you, I get goosebumps. think of a passing of a torch, and nothing could be more monumental than something like that. Passing of a torch. Think about that for a moment. 1642, Isaac Newton. And life on this planet changed after this particular individual. We're going to take a jump. 1803, another jump. John Dalton. Remember the partial pressures guy?
Yeah.
John Dalton. John Dalton says, okay, I think we've got something. And he writes his atomic theory. And he says some tenets of atomic theory, some of which are right and some of which were actually wrong, but there was no way that he could know that ahead of time. Think of the day. This guy was a genius ahead of his time. And he said things like, Democritus was right. And things are made of atoms, and these are indestructible. That's a problem, because we know that not to be true. How do we know that that's not true? He didn't know that back then, but we know now that's not true. Why? Because we know that, right? He said all the atoms of the same element are the same. Also almost right. But we know this to be somewhat wrong. Why is that? Because we know now all about isotopes. because now we know all about isotopes. Is that okay? Reactions are just the rearrangement of atoms. That's true. So of all the things that John Dalton said, it was an incredibly great start for chemistry, because we finally shook a theory that had driven chemistry down into the Middle Ages and kept it down because it persisted and it was complete crap. On your own, if you really are interested and you are an enormous geek, you can look this up. The geek factor is high if you look that up. Okay, so this is a theory that kept humanity in the dark for hundreds of years because people insisted on this particular theory, and they were dead wrong. John Dalton was on the better track. We good? So 1865 comes around. A guy by the name of Maxwell. Works on certain equations, and you guys might run into these equations in physics and engineering classes and thermodynamics classes, some upper division classes you run into this. And Maxwell defines light and defines electromagnetism. And he says energy is equal to Planck's constant times a frequency. Remember the formulas that I put up you're responsible for. Not just the names, but the formulas, because we're going to work with these. This is Planck's constant, and that's a frequency. That's a frequency.
It's like a backward C.
No, it's a cursive U. Bring down a straight line, and now turn it.
That looks like a D.
And it is a Greek letter
It's half of
Nu.
D.
Like in I have a new computer. Nu. And nu is a symbol for frequency. And while we're at it, what's the symbol for wavelength? Lambda. Lambda. This is wavelength. Frequency, the Greek letter nu. In the books, they usually put it as a cursive V. It's like a little cursive V, but what it is that. Bring down a straight line and turn it. Electromagnetism. Now we're getting somewhere. Light is a wave that has frequency and it has wavelength. The H is a constant, and you guys are going to memorize it. H is a constant, and you guys are going to memorize it later. We're going to do problems on this. And you guys are going to memorize it. 6.63 times 10 to the minus 27 or 34, depending on the units. Let's not do that now. We're going to do problems like this. 1865, in Poland. There's a young girl. And her name is Mania Skłodowska. And she's having a hard time. Her sister, her older sister, her mom died when she was 10. And her older sister was already studying to be a doctor in Paris at the Sorbonne. And she had a job as a babysitter, but she wasn't much older than the kids she was watching. You know how that goes. The family was poor, so she had to work. And she made a horrible mistake. She fell in love with the oldest boy in the family. And the family would not have it because the boy loved her back. And that's a problem. So they threw her out of the house. Incredibly depressed, she writes in her journal, I don't know what's going to become of me. If I die today, regret for me will be short. What does that sound like? It sounds like she doesn't care much whether she lives or dies. It sounds like a typical teenager, doesn't it? A little emo, if you ask me. A little emo. And this is 1865. Her sister writes her back. You blah, 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 and blah, blah, blah. Get your act together. You should make something of yourself, she tells her younger sister. Quit whining. Come with me to Paris. And she says, well, maybe. I'll think about it. Maybe. 1870. Dmitri Mendeleev. Dmitri Mendeleev, the 15th child of a Siberian family. Yeah. Mrs. Mendeleev thought her son was very smart. And she said, I'm going to get this boy an education no matter what it takes. So she grabs it. Her husband had died. Factory burned down. They had a glass bottling factory burned down. It sounds like a country music song. My farm burned down. My husband died. All true. All true. You can look this up. I swear to God, I make stuff up, but I swear to God, not this. You can look it up. So she grabs Dmitri, age about 15. And Dmitri had been befriending prisoners in Siberia. And one of the prisoners taught him chemistry, and Dmitri thought that was just the greatest thing ever. What kind of prisoners do you think a mom would let a child hang out with? It's Siberia. It's the 1800s. What do you think they were sending to Siberia? What kind of prisoners?
War prisoners.
Political prisoners. So they weren't really bad guys. They were just burying them in some godforsaken place where nobody would be hear from them. So one of them knew chemistry, and he taught Dmitri, and Dmitri thought it was just great. Mom says, hey, this kid's smart. Goes to Moscow University and says, hey, this is my son Dmitri. Would you know, he's really smart. So says his mom, right? And they said, no, actually, we don't take his kind here. What do you think his kind was? Not a white Russian. Who lives in Siberia? Not the white Russians. So she said, oh yeah, watch this. She goes to a different university, and there she knew a guy who knew her husband. He says, hey, this is Dmitri. Remember me? I'm Mrs. Mendeleev, and he's really smart. You know I'm telling this story kind of fast, right?
Yeah.
Okay. So they said, oh, Mrs. Mendeleev, don't worry, leave me the boy. It's wonderful, good to see you. Just leave him with me, and I'm going to take care of him. And they say, Dmitri, very nice. Get in the lab. Go wash those dishes. Hey, you got to wash dishes at some point, right? This week is the floor, next week is the fries. That's how it goes in chemistry too. It's universal. So Dmitri very slowly starts moving up in the food chain. Amazing lab work. Spends all of his life in the laboratory. And you know what he does, right? You know. What does he do? He orders a periodic table. Not exactly in the way that you see it now, but pretty much. He said, listen, stop ordering things by how much they weigh, because you're making a mistake. Look at tellurium and iodine. Which one weighs more? Tellurium, but he's ahead of iodine. And what did he say? He said, listen, fluorine, chlorine, bromine, and iodine all react the same. Stop the stupidness of putting them with how much they weigh. He says, I don't know why it should be so. I don't know why. Because they didn't have these numbers. These ones, they didn't have. All they had was a weight. So he said, I don't know why, but I'm telling you that we're wasting time if we don't put them in columns where it makes sense, where the properties go vertical up and down. So stop with the stupid stuff of jamming these guys all the way over here. They don't belong there. Get them out of there. Put these guys in order, and I'll give you another one. Do you see this one here? He left it blank. And he called it Eka aluminum. Eka is a Sanskrit prefix for the first element after aluminum. Eka aluminum. And he said, I don't know who's going to find it, but leave it blank because we don't have one that fits there. And it's going to have this property, this melting point. It's going to look like this, and it's going to do this, that, and the other. Up to that point, everybody thought that Russian chemistry was like, those guys are crazy. Especially that one. Who doesn't shave, who never cuts his hair, not even when the Tsar calls him to talk to him. And he looks like hell all the time, and he does not give a flying rat's ass. Look at all his pictures. They are crazy. And and he enjoyed that. So he said, especially that crazy guy. So guess what they found? Eventually, they found the element that fit there. And it had exactly all the properties he predicted. So from then on, they said, "Ha, how do you like me now?" And then he was famous, and you know his name, Dmitry Mendeleev. Dmitry Mendeleev. So Manya
I wouldn't mess with that.
grabs a folding chair, a blanket, some food, a water bottle, and the only money that she could get together, and her dad gave her as much money as he could, and she goes on a train to Paris. Parisian society is very different for her. She's a girl from Poland. She's not used to this stuff. So she says, I want to fit in, and this whole Mania Skłodowska is not working for me. So I'm going to change my name to Marie. So I'm going to change my name to Marie. Marie actually turned out to be incredibly brilliant. And when she shook her emo phase, she actually started working in a lab. Nobody wanted to give her a job because she was a female. And they said, hey, I know of a place. If you don't mind working with this weird guy, he's a little strange and he works with his brother, but he's very nice. So won't you go over there and see if they have a job for you, something for you to do in the lab? So he knocks on the door, opens the door, and there he was. There he was, Pierre. I swear to God, his name was Pierre. I know it sounds cliche because it's France and everything, but his name was really Pierre, I swear. And his brother's name was Jacques. I swear to God, I'm also not making that up. I know it sounds bad, but I swear that's what their names were. And Pierre was 36 years old. He had already concluded that no woman could ever attract him because he could never find anything interesting to talk to a woman about. And in comes Marie. She opens the door, and what do you think he said? Hey now. In French. Mon Dieu. Right? So they give her a job. And what do you think? Let's see. Do you guys think you know Pierre's last name? You betcha. Curie. So a few years later, in 1897, they married. Yes.
Marie Curie.
They bought bicycles for their honeymoon. She wore one dress and one dress only, and she said, if anybody wants to give me a wedding dress, make it a black one, so that I can keep using it in the lab, because this whole thing of white dresses, they all get very messed up, and I don't have any use for things, because then I have to dust them. I'd rather be in the lab. So if you ever visit Paris, please visit the Curie Institute, where I have pictures on the website that I sent some of you. Look through those photographs, and the Curie Museum, her dress is there. Yeah, I took pictures next to her image and stuff like that, and you can do that. I think it's free or very, very cheap to go into the Curie Museum. Okay, so 1897, 1895, the discovery of the electron. J.J. Thomson. The discovery of the electron by J.J. Thomson. The discovery of X-rays by Röntgen. The discovery of X-rays by Röntgen. The discovery of radioactivity by Pierre's best friend, Henri Becquerel. They kept radioactive materials in their pocket to show and tell at parties. Their notebooks are still dangerously radioactive until today. To go in certain parts of the museum, you have to sign a release. They kept it as a nightlight on their table, on their little night table, because they glow green, very nice. They called it faint fairy lights. And they kept it in their pockets. Marie herself died at the age of 62. After winning 2 Nobel Prizes, her daughter won 1 more, and she died of aplastic anemia, which is a side effect of radiation. Pierre, unfortunately, wasn't that lucky to live that long. Pierre died on a Paris afternoon, and a rainy Paris afternoon, April 19th. of that year, his children were very, very small. He was in a rush to go to a meeting. They had constructed brand new labs for them. They had won a Nobel Prize. They were on top of the world. And they were really happy to be able to get back to work. He and Marie were. He rushed across a Paris street and got hit by a truck carrying 6 tons of military uniforms. And he was killed instantly. She was crushed, absolutely devastated, because they had, by all accounts, a really, really great marriage. So Pierre died way, way before his time. If he had lived, he probably would have died of the same kind of disease that killed most of them, because they didn't know about the side effects at that point. So, 1911. Ernest Rutherford, a student of J.J. Thompson. Ernest Rutherford, a student of J.J. Thompson. All this stuff, guys, all this stuff is at the beginning of chapter 4. You need to know this by Wednesday. Don't waste time. Discovers the nucleus of the atom. Discovers the nucleus of the atom and does the famous gold foil experiment. The items that are inside of an atom are starting to become interesting to people. Humans have now decided that this atom is a big question mark. And people are starting to wonder, much like the Greeks that started asking questions, hey, what's everything made up of? Earth, wind, fire, and water? Yeah, right. They started saying atoms? Okay, Democritus, you were right. Okay, Dalton, you were right. But now we have to find out what that's made up of. They begin to do experiments, and Rutherford's directions to his students is as follows. He says, get a piece of material of different metals. Lots of different metals. And everybody talks about the gold foil. So imagine like aluminum foil but made out of gold. And what do people do when they don't know what something is? They throw stuff at it. They throw stuff at it. So they part a piece of gold. And with gold, they do a lot of other materials as well. In front of a scintillation screen, in front of a screen, back here, they get a box with a radioactive material that shoots alpha particles. Radioactivity comes in 3 flavors: alpha, beta, and gamma. Of the 3, which one's the most dangerous? Gamma radiation. This one's somewhere in the middle, and alpha particles are less so. We'll talk about this later. He sets up a material that's going to throw alpha particles in that direction. What they thought was going to happen